Welcome to WikiPodcast. Welcome to the deep dive. We are plunging into, well, the really fascinating world of sound waves today.
Yeah, exploring how a simple thing, just a vibration, can turn into everything we hear: music, noise, speech.
Exactly. This is part of our ongoing physics series, looking at waves, sound, and light. And today, it's all about sound waves, how those vibrations become music and everything else.
That's right. We've been diving into the physics articles, research notes on acoustics, perception,
Right.
really trying to map that journey
From a physical ripple.
to an experience in your head. It's quite a trip.
So our goal here is to pull out the key ideas, connect the sort of hard physics to how we actually perceive sound.
And hopefully find some of those aha moments about something that's happening around us constantly.
Yeah, like think about hitting a drum or just snapping your fingers. What is actually physically happening there? Let's get into it.
Okay.
So physics first. At the most basic level, what is sound?
Well, fundamentally, it starts with a vibration. Something has to wiggle or oscillate. And that wiggle travels. It propagates as an acoustic wave through some kind of medium.
Like air.
Air, water, a metal pipe, your skull.
Yep.
Anything with particles that can be disturbed. The source, like a speaker cone moving back and forth, creates that initial disturbance.
Okay, but you mentioned perception. That physical wave, that's not the whole story, is it?
No, not at all. And this is a really key distinction we found. There's sound as the physical phenomenon, the wave existing in the medium, and then there's sound as the sensation, the reception of those waves by your ear and the interpretation by your brain.
Ah, the old tree falling in the forest question.
Exactly. Physically, yes, the vibrations and waves are absolutely there when the tree falls.
But if no ear, no brain is there to process it.
Then from a perceptual standpoint, you could argue there was no sound, just potential sound maybe?
And our ears, they have limits, right? We don't hear all vibrations.
Definitely not. Human hearing typically covers a range from about 20 vibrations per second up to around 20,000 vibrations per second.
And we measure that in hertz. So 20 hertz to 20 kilohertz.
Precisely. 20 hertz is a very low frequency, like a deep bass rumble you might almost feel.
And 20 kilohertz.
That's a super high-pitched whine. It's often the upper limit, especially for adults, as that range tends to shrink a bit as we age.
And what does that mean in terms of the actual wave size in air?
It's quite a difference.
Right.
A 20 hertz wave is huge, physically about 17 meters long from peak to peak,
Wow.
whereas a 20 kilohertz wave is tiny, only about 1.7 centimeters.
So vibrations outside that range, they still exist.
Oh, absolutely. Faster than 20 kilohertz is ultrasound. Think medical scans, dog whistles.
Right.
And slower than 20 hertz is infrasound. We might feel it as pressure pulses sometimes. Animals like whales, elephants, they use infrasound to communicate over really long distances.
So different animals perceive different slices of this whole vibration spectrum.
Exactly. And the science that studies all these mechanical waves, vibrations, sound, ultrasound, infrasound, that's acoustics.
It sounds like a huge field.
It really is. Super interdisciplinary. Touches on physics, engineering, psychology, biology, music, you name it.
Okay, so how does the vibration, say, from my voice right now, get across the room to a microphone or someone's ear? The air molecules aren't flying over, are they?
No, that's a common misconception. The air molecules themselves mostly just jiggle back and forth in place. They bump into their neighbors, passing the energy along, but they don't travel with the wave.
Ah, like doing the wave in a stadium.
That's a perfect analogy. The wave travels around the stadium, but each person just stands up and sits down. They aren't running around the track.
Got it. So it's energy transfer.
Exactly. Energy transfer through the medium. There's a classic physics demo with two tuning forks.
Oh, yeah.
You strike one, it vibrates. The vibrations travel through the air. If you bring a second identical tuning fork close, the energy carried by those air vibrations can actually start the second fork vibrating visibly.
Cool. Shows the energy moving, not the air itself.
Precisely. And these waves, they can travel in slightly different ways.
Yeah.
In gases, like air, and also in liquids, they travel as longitudinal waves.
Longitudinal? What does that mean?
Think of it like a slinky you push and pull.
Mm-hmm.
The coils bunch up, that's compression, and then spread out, that's rarefaction. These compressions and rarefactions ripple along the slinky.
Okay.
The key thing is, the particles are vibrating back and forth along the same direction that the wave is traveling. Push-pull.
Right. And in solids.
Solids are special. They can support both longitudinal waves and also transverse waves.
Transverse. That's different.
Yeah. Think of shaking a rope up and down. The wave travels along the rope, but the rope itself is moving perpendicular at right angles to the direction of the wave, like shear waves.
Why only in solids, mostly?
Because transverse waves need the medium to resist being sheared or twisted. Fluids, like air and water, don't really do that. They just flow. Solids resist.
Makes sense. And a key point, sound needs something to travel through, right?
Absolutely essential. It needs a medium. Gas, liquid, solid. It cannot travel through a vacuum.
This is space movies getting the explosions wrong.
Pretty much. No air, no sound. The vibration has nowhere to go.
And as these waves travel, they can bounce off things.
Yep, reflection, that's how you get echoes. They can also bend or refract if they pass into a different medium or temperature, and they gradually lose energy, they attenuate, which is why sounds get fainter with distance.
What affects how fast they travel?
Primarily the properties of the medium itself, its density and its elasticity, or how springy it is. Temperature is a big factor in gases too.
Warmer air means faster sound.
Yeah, roughly.
Right.
The formula is about 331 meters per second at freezing,
Okay.
plus about 0.6 meters for every degree Celsius warmer. So around 343 meters at room temperature, 20 degrees C.
And in other stuff.
Much faster in liquids and solids, typically. Around 1480-something abs in water, almost 6,000 meters in steel.
Wow, that's fast.
It is. And the theoretical fastest is in solid atomic hydrogen, maybe over 36,000 meters.
Crazy. Okay, so these waves create pressure changes, which relates to loudness.
Exactly. Sound pressure. It's the tiny, tiny difference between the normal atmospheric pressure and the pressure caused by the wave's compressions and rarefactions.
Tiny.
Incredibly tiny for quiet sounds, but the range our ears can handle is immense. From the threshold of hearing to sounds that cause pain, the pressure difference spans a factor of millions.
Which is why we use decibels, DB.
Right. It's a logarithmic scale. It compresses that enormous range into manageable numbers. It's based on ratios, not absolute values.
Right.
A 10 dB increase is roughly perceived as twice as loud.
And you often see dB/SPL or dBA.
SPL just means sound pressure level, indicating it's measured relative to a standard reference pressure, usually 20 micropascals in air. The A in dBA refers to A weighting.
Weighting.
Yeah, it's an adjustment to the measurement that accounts for how sensitive the human ear is to different frequencies. We're most sensitive in the mid-range, less so at very low or very high frequencies. A weighting tries to mimic that, so dBA levels often correlate better with perceived loudness or annoyance.
Okay, so that covers the physics side. The vibration, the wave, propagation, speed, pressure, the objective stuff.
Pretty much the physical event itself, yes.
Now let's cross over to that second definition. Sound as the experience. Perception.
Right. This is where psychoacoustics comes in. How does your brain take those physical pressure waves arriving at your eardrum and turn them into, well, sound as you know it?
And it's not just about music or speech, is it? Sound is crucial for survival, navigation.
Absolutely. Detecting danger, locating things you can't see, communicating animal calls, human language, even just understanding our environment, wind, rain, a car approaching. We've built technologies like phones and radio entirely around manipulating sound for perception.
What about noise?
Often defined as unwanted sound, right? But perceptually, noise is also information. The type of noise helps identify a source, a hiss, a scrape, a buzz. It's part of a sound's character.
And the overall sound environment.
We call that the soundscape. Everything you can perceive acoustically around you.
So how does the brain break down these incoming waves? What are the sort of perceptual building blocks?
Research suggests there are about 6 main ways we analyze sound perceptually. First is pitch.
High or low?
Exactly, how high or low it sounds. This is primarily linked to the fundamental frequency of the vibration. Faster frequency, higher perceived pitch. Your brain is analyzing that repetition rate.
Is it always just the main frequency?
For simple tones, mostly yes. For complex sounds, like a musical note, it's usually the fundamental frequency. But the brain also looks at the pattern of harmonics, the overtones.
You mentioned white noise sounding higher than pink noise before.
Yeah, good example. White noise has equal energy at all frequencies. Pink noise has equal energy per octave. So white noise has much more energy in the higher frequency bands overall, and our brain interprets that as having a higher pitch quality.
Okay, second element.
Duration. How long or short a sound seems. This involved the auditory system detecting the start, the onset, and the end, the offset of the sound signal.
And perception isn't always literal here either.
No. For very brief sounds, say under 200 milliseconds or so, shorter sounds actually seem quieter than longer sounds of the same physical intensity. That's called temporal summation.
Interesting.
And get this. If a sound is briefly interrupted, maybe by a gap or dropout, but that gap is filled with noise that's spectrally similar to the sound,
Yeah.
your brain can actually fill in the gap and perceive the original sound as continuous.
Wow. Like noise canceling out the silence.
Kind of. It masks the offset signal that would normally tell your brain the sound stopped. It's part of why we can understand speech on a noisy phone line. Our brain perceptually restores the masked parts.
Amazing. Okay, number 3.
Loudness. How loud or soft it feels. We link this to physical sound pressure, the amplitude.
Right, decibels.
But perceived loudness isn't just about amplitude. It seems related to the total number of nerve firings in the auditory nerve over short time windows, maybe around 200 milliseconds.
So higher pressure means more nerve firings, louder sound.
Generally, yes. But it also means a complex sound, like music or noise with lots of frequencies, can trigger more nerve firings overall than a simple pure tone at the same physical amplitude, and therefore sound louder.
Okay. Complexity matters too. 4th.
Kimbra is a big one, often called sound quality or tone color. It's what lets you distinguish a violin from a flute playing the same note, or recognize a specific person's voice.
How does the brain figure that out?
It's incredibly sophisticated. Timbre perception involves analyzing a whole bunch of things simultaneously. The pattern of harmonics and overtones, how noisy or breathy the sound is, how steady the pitch is.
So it's a snapshot of the sound.
Not just a snapshot. This is crucial. Research really emphasizes that how these features change over time provides the most important clues for identifying timbre. The attack, the decay, the subtle fluctuations.
So how a sound evolves tells you what it is.
Exactly. A piano and a clarinet playing the same note might have a similar-looking waveform if you freeze a tiny instant. But the way the sound starts, the percussive hammer strike versus the gradual swell of air, and how the harmonics change as the note sustains and fades, that's the key information.
Got it. 5th element.
Texture. This relates to the number of distinct sound sources you perceive and how they interact.
Like layers of sound.
Sort of. It's about your brain's ability to cognitively separate different auditory objects. In music, you might hear one voice, monophony, chords supporting a melody, homophony, or multiple independent melodies woven together, polyphony.
And outside music.
Think of a busy cafe. Your brain tries to separate individual conversations, the clatter of dishes, background music.
Yeah.
That overall sense of complexity and layering is texture. It might be perceived as cacophony if it's too much.
Okay, and the last one. Number 6.
Spatial location, where you perceive the sound coming from.
Left, right, up, down, far away.
Exactly. Your brain calculates this using subtle differences between what arrives at your two ears. Tiny differences in arrival time.
Enteral time difference.
Yes. And differences in loudness or frequency balance.
Interal level difference.
Right. Especially for higher frequencies, where your head actually creates a sound shadow. Plus, it interprets reflections off surfaces to gauge distance and the nature of the space, like reverb.
And this helps sort out complex scenes.
Hugely. Combining spatial location with timbre is how you can focus on one person's voice in that noisy cafe. Your brain uses where it's coming from and what it sounds like to pull it out from the jumble.
Okay, so let's pull this all together. We have the physics, the objective vibration, the wave properties like frequency and amplitude.
The raw ingredients traveling through a medium.
And then we have our auditory system, ears and brain, acting like an incredibly sophisticated processor.
Taking those physical pressure variations and transforming them, translating them into these subjective, meaningful perceptual qualities. Pitch, loudness, duration, timbre, texture, and place them in a perceived space.
It really is an amazing bridge between the physical world and our conscious experience of sound.
Absolutely.
So why should our listeners care about all this? What's the takeaway for everyday life?
Well, I think it gives you a much richer appreciation for just how complex everyday sounds really are, why music affects us the way it does, why different instruments sound unique.
How we know where things are just by listening.
Right. Or even how engineers design things like concert halls for good acoustics, or headphones and speakers to reproduce sound accurately. It's fundamental to how we interact with and understand our world through hearing.
It really is everywhere.
So maybe something for you to think about. Given that sound, physically, is just these pressure waves, these simple vibrations moving through air or water, whatever, how does our brain manage to translate that relatively simple physical phenomenon into something as incredibly complex, rich, emotional, and profoundly meaningful as music?
That's a deep one. How does physics become feeling?
Yeah. How does vibration become Beethoven?
Thanks for listening. Write us your opinion in the comments on our letter questionnaire. Given that sound is just physical vibrations propagating through a medium, how does our brain manage to translate those simple pressure waves into something as complex, emotional, and meaningful as music? Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.